Welcome to the webinar. We're here to talk about maximizing the power of Gaudi2. My name is Greg Soraki. I'm part of the Habana Applications Engineering team, and I'm based in Portland, Oregon. I have Moet Diopajari and Harshvardhan Chauhan, also part of the Applications Engineering team. And we're going to spend the next hour and maybe a little bit over talking about the fundamentals of Gaudi and Gaudi2, a product we're really proud of. In the workshop today, we are doing this on Zoom. So we have the question and answer category here. So the session's being recorded and we'll post this on the developer website. So you can take this, if you can't stay for the whole time, you can come back and watch a recording of this later. If you have any issues or questions during the time here, please use the question and answer capability in Zoom, and we will be talking about these and answering your questions while we have some time during some of the demos, and then we can answer some stuff real time, as well as at the end, we'll have some Q&A time as well. All right. Yes, we'll talk about CSP adoption at the end of the presentation, Jim. Okay. So our objectives today, this is really an evolution of our Getting Started workshop. So we originally started with some really basic things, but for Gaudi1, and we've been doing these workshops for about a year. So the objective today is to really go to that next level. So we want to introduce Gaudi2, which is really where all of our focus is today. So we'll talk about Gaudi2. We're going to do three main things with Gaudi2. One, we're going to show inference on a generative AI model, and that'll be really fun. We'll talk about model migration and what does it take for you as a user to take a model either from our GitHub page or from Hugging Face or from another public model. If you're using a model on your own in your business, how do you migrate that to work on Gaudi2? And then finally, we'll show running a large language model. And what does that take? Both taking it from fine-tuning the model and then running it on inference. And we'll show that using Deep Speed, which is really the key, one of the key software libraries that we use to help ensure that a model can run on multi-cards and multi-nodes and really scale with high efficiency. So that'll be our objectives today. So let's first talk just really briefly about Gaudi and Gaudi2. Let's remember that the Gaudi family here is not a GPU. This is a dedicated AI processor that was designed from the ground up to be designed for deep learning inference and training. So we look at one of the key things that's really a differentiator about Gaudi2 from the competition is its integrated Ethernet ports. And we see now on Gaudi2, we have 24 100 gig Ethernet ports. And this allows full connectivity on the board in a single server, where we have 8 Gaudi2s fully connected, as well as for a high-speed connectivity directly out to other nodes in the rack or other switches, depending upon the infrastructure. We have 96 gigabytes of onboard high bandwidth memory. So this really allows us to scale up and train on larger and larger models with much more efficiency. We have Gaudi2 available in the Intel Developer Cloud. So this is Intel's own proprietary data center that we have available for people to sign in and use. And so Gaudi1 is available on Amazon and AWS as the DL1 instance. So if you want access to Gaudi, you go to AWS. If you want access to Gaudi2, you go to the Intel Developer Cloud. And I'll have links to both of those at the end of the presentation. So again, the really key part here about Gaudi2 is really the evolution of Gaudi, the 96 gigabytes of onboard high bandwidth memory and 24 100 gig Ethernet ports for really driving high performance and large models. And then we also have solutions here. We partner with Supermicro to also include on-prem solutions that you can actually buy full chassis and full systems from Supermicro with Gaudi and Gaudi2. We look at the workloads here. We really focus on three main areas: computer vision, natural language processing, and multimodal. Obviously, the big push right now has been on natural language processing. So things like now ChatGPT, GPT-3, GPT-based models. So all those things that we see people doing in the industry today, natural language processing is that focus. Multimodal here is where we're using a combination of video and text to be able to have a deeper user experience. So we have models there as well. And then in terms of the verticals, you see there at the bottom, we have some examples on our GitHub page that show examples on how to do fintech, autonomous vehicle, vision training and fine tuning, and computer vision use cases as well. And we also have a chat use case as well. So we're really focused on these really key use cases that everyone is interested in today. Now, how to execute that is through our software suite. And so our software suite is called Synapse AI. And the key takeaway here is two things. One, this is our shared software stack for both training and inference. So you use this and it covers both. And it is integrated with PyTorch and TensorFlow. So you bring your PyTorch model or your TensorFlow model, you plug this into the Synapse AI software suite, and your model will run. This is optimized for deep learning with minimal code changes. So internally, we have a bridge that bridges between PyTorch and TensorFlow, our own customized graph compiler, and communication libraries. So this is based on the NVIDIA communication library. We call this HCCL, so the Habana communication library that we use. So it is basically a copy of the Nickel library. We have a huge set of kernels, as well as our own kernel library that you as a customer have the opportunity to write your own kernels for that final step of fine-tuning and performance to be able to add that into the software stack. We also provide you with fully encapsulated Docker images. So the thing that makes it really easy to use here is once you get access to a node, either Gaudi1 or Gaudi2, we provide you with a suite of PyTorch and TensorFlow Docker images that make it really easy to get up and running and started. So you have PyTorch, you have TensorFlow, you have all of our software preloaded. So once you run that Docker image, you're immediately ready to start running models and start training or start running inference. And built on top of that is our community and ecosystem. So we have our Habana developer site, our GitHub, and our forum, which we'll show you in just a few minutes. So again, the key takeaway is Synapse AI software suite is built for PyTorch and built for TensorFlow. Now, our model references. This is our GitHub page. Our GitHub page now, we have over 50 models across a range of computer vision, natural language processing, generative AI, and large language models that you can use as a reference for your work. So you can, and these models are fully optimized and fully performant on Gaudi and Gaudi2. So the benefit here is this is a great jumping off point for you to investigate how to get these models running on Gaudi, to use them as a baseline for your own investigation and use, and simply just use them. So we have a set of both PyTorch and TensorFlow models. Although we'll admit that over the last year, our focus really has been on PyTorch. Okay, so let's jump in and look at one of those models in action and look at a demo. So what I'm going to show you now is our stable diffusion model. So when we look at our GitHub page, let's start here at our GitHub page, and we'll go to our model references. And you will see here, as I showed you, a huge list of models. And let's look at our generative model here. So we have several stable diffusion models. Let's pick the latest one, 2.1. And so in this case, we have our stable diffusion model. And all of the instructions you need to run this are all fully included here. So what we'll do is we have that running now in a Jupyter notebook. So what we're doing now is running on a Gaudi2 system, and we are running a PyTorch Docker image, and we've initiated a Jupyter notebook, or Jupyter Lab in this case, running in our Docker. So we will clone the model references, which I've already done. And let's go to the generative models page in our model references. We need to set the Python path to point to the content of this page. So we will do that. We'll install the requirements. So there are additional, each of these models has its own additional libraries that are needed to be able to run. So those are run. We download the checkpoints. In this case, I've already pre-downloaded those, so we will skip that step, but it takes about 90 seconds. We'll skip it. Now, in this case, we have everything we need to run the model. So now we have the model loaded, we have all the requirements pre-installed, and we have the checkpoint. So now let's input a prompt. So I'm going to use a little Ocean's 11 reference here. So I'm going to say George Clooney and Matt Damon at a casino. And now the script that actually runs this is called text-to-image.py. So this is a Python image or Python script that takes that text prompt that I just entered and uses Stable Diffusion to create the picture. So let's look at a couple of the commands that we're passing in. In this case, we are using the prompt that we just collected a moment ago. We have the checkpoints here that we downloaded from Hugging Face. There's a YAML file here that sets some of the deeper configs. In this YAML file, you have the ability to modify some of the configs, but we use the default values here. So for you as a user, unless you're really looking to fine tune something, there's no changes you need to make. We set the height and width in pixels of the picture we want to output, the number of samples, iterations, and steps, and some of the sampler settings are here. These are the default values. And finally, we use HPU graph. So HPU graph is one of the techniques that we have built into the Synapse stack to help drive additional performance and help prevent recompilations. So now we see this running. We always get this PyTorch bridge configuration. So you see this information that's provided to you for reference. And all the steps are now complete. And now we have the file saved off in the outputs directory. So let's take a look at what it looks like. And there we go. So that's pretty cool. And this is, so again, you can take this and use this to generate any content you like. This is the great party trick that we all like to do. Some of you maybe have done this with Midjourney or other models. Once you have access to Gaudi, you can just do this on your own. All right. So now that we're done running the model, I'm going to hand this off now to Harshvardhan to tell us how we can do the model migration. Harshvardhan, the floor is yours.
Yeah, I'll share my screen. Okay. I hope you can see my screen. So the model migration steps regarding, so let's say you have a model which is at your end and you want to run it on HPU or on the Gaudi. So we're going to talk about that. But firstly, I'm going to cover three main sections over here. One thing is that we have a lot of models that have been implemented at our end. I think so, which you just saw Greg mentioned about at our GitHub repository. So we have like a huge resource and collection of models that you should go ahead and try. And that's what we have enabled specifically to run on Gaudis. They are fully optimized, and these have been covered in the section of computer vision, NLP. So that's one section. There's the another one wherein there's a collaboration with Hugging Face with an optimum Habana library interface. So you can run any transformer model using optimum Habana library, which we're going to talk more in depth in the coming slides. And the third one, which I want to focus right now, is let's say you have your own model. Mostly folks are running on GPU, and how do you want to convert a CUDA-based model on which can be compatible with the HPU? So let's go through that. So first, I want to cover specific pointers about manual model migration. Let's say you have a model CUDA-based, which is written in CUDA, and how you can run that. So first step is definitely you want to remove the CUDA calls. Second thing is the import of the Habana Torch library. So you want to focus upon importing the library, the HT core. So this is the main import that you would do that would help you enable to run the models on HPU. The third step is that you want to import the mark step after the loss calculation as well as the optimizer step. So how this works is the mark step is that in the case of model migration, in lazy mode, which allows Gaudi to collect ops and only run these steps when needed. So instead of running every single step every time, what we are just doing is, which could cause a slowdown in your performance, it's just aggregating the ops and running them when needed. Third thing that you want to make sure is that your device is pinned down to HPU and not to CPU or GPU. So you want to make that particular change right up over here. There is then autocast, and for mixed precision training, you just want to make sure that the device over there is again set to HPU. And the fifth is for distributed training. We make sure that our backend is set to HCCL. I hope you folks just went through the HCCL in our software stack part at the Habana communication library instead of NCCL. So we make sure that the distributed data parallel model specifically gets run on the HPUs, the Habana processing units. Now, we have designed a GPU migration toolkit to make your task a little bit easier. This GPU migration toolkit, what it does, it helps you to map specific API calls from Python libraries and modules like torch.cuda, torch API with GPU related parameters, Apex, and PyNVML. I want to focus on these two ones specifically over here, the torch.cuda and the torch APIs. Now the GPU migration toolkit is pre-installed. Any Docker that any version, the latest version is 1.10 that you install, it just comes pre-installed in it. So you do not need to worry about any other installation. Now the GPU migration logging, this is something that you want to, I want to highlight up over here, that you can activate these logs to understand that how these migrations are happening from CUDA calls to HPU, and this could help you in debugging. You can set this parameter to value 1, 2, or 3, depending upon how you want it to print, like on your terminal, or you want to save it in a file. So with the PyTorch migration with the GPU toolkit, how does it make migration of a model simpler? So it's just 2 steps. So in the manual migration, you saw that you need to take care of a bunch of things, but over here, all you need to do is just import the Habana framework, the torch.gpu migration. You want to make that call, as well as import, obviously, the Habana torch library up over here. And you want to make sure that you place the mark steps that we discussed earlier after the calculation of loss and after the optimizer step. That's it. You are ready to go. Now, what I want to do is I want to show a model migration demo. So let's jump into a Jupyter notebook. So this the crux of this Jupyter notebook is that we have taken a ResNet 50 model based on PyTorch, and this is an open source implementation of ResNet 50 on CUDA. All that we have changed up over here is used our two pointers that I mentioned in the last slide, and boom, that's it. The model is ready to go. So let's run this. What I'm going to do is I'm going to clone the model references. So over here, the model is present. It should clone up like really fast. So we are going to use the model right from our model references GitHub repository, which has been present over there. Okay, so once this has been cloned, I'm just going to set my environment variables, Python path, the Python, and I'm just going to navigate into the folder where this model is located. And I'm not going to download the data sets because the data set, I already downloaded it. It's ImageNet data set. This is a pretty famous data set. So you can still go down, when you run this particular model from the Jupyter notebook, install it at your own end, and you should be good to go. And next, I want to take a moment over here and just let you know that what are the specific changes that we have made in this particular code. So in the train.py file, as I mentioned earlier, what we want to do is at the top, we want to import the GPU migration toolkit right here. And what we want to do is we want to import our Habana PyTorch library, so which is right up over here. So this was the step one. And the step two was we want to place the math steps after the loss as well as the optimizer step. So that's what we have placed down up over here. So just these are the two changes that we have done to the code. And then all we do is we run the command to train. So this is the command that we are using to train. A few things that I want to highlight over here is, so I'm using the flag, which I mentioned earlier, the GPU migration log level. I'm setting it to 1. What we would do is it would just give out the logs directly on the terminal up over here. So I can show you like how some of these specific calls are being made and the conversion is happening. I'm just running this for one epoch because the goal is not to train the model, just to show that how it works. Device is set to CUDA, even though like we are running this on HPU. So you'll see like how this actually works. So yeah, let's go ahead and run this particular command. Okay, so since this has started running, few things I want to highlight up over here is you can see that how does this API call handles the conversion. So there is an HPU match. There are basically 3 API calls. API calls are 3 different types. I'm going to talk in a little bit depth in a while. You can see the HPU match. What it happens is, in the code, there's like torch.cuda set device. It's converted it to torch.hpu. And then for the backend, you can see that because since we are doing the distributed training on 8 cards, right up over here, the backend from NCCL is being changed to HCCL, our Habana communication library. It is doing it for all the cards. You can see for device 1 to 7. And so you can see like how these changes, these calls are being made. The GPU toolkit is handling this for you and making this very much easier as part of the model migration steps. I'm just going to scroll past because these are some of the other calls that it's making. You can just see right up over here how these calls have been made. So once it gets initialized, goes past through initialization of model and everything, and right up over here, it starts to train. So you can see right up over here, the training has started. It's going to run for 1 epoch. While this is running, I just want to go back, take you to the slide. And what I want to show is, as I mentioned earlier, like the Python APIs for GPU migration toolkit are classified into 3 parts. One is the HPU match, which you just saw. So what happens over here is it maps GPU arguments to HPU arguments, or the GPU output value to HPU output value. Right up over here, you can see an example. If you have a call like something like this, how it would, the GPU migration toolkit would take in and convert the device from CUDA to HPU. Now, there is another scenario wherein you would encounter is HPU modified. So what there is, like, we have made sure that certain Habana specific calls have been used to replicate GPU specific functionality for the sake of compatibility. So let's say you have called something like tosh.cuda float tensor, how that would get connected and mapped onto the HPU. Now there's a third scenario where what would happen is you can encounter HPU mismatch. Now what would happen in that case scenario is either the call would be made as inactive, or it would throw a non-implemented error exception. In such case scenario, what you would do is, if there is an HPU mismatch, you would activate the logs, which I mentioned up earlier, and see where specific or on what specific call it's throwing an error, and use this particular table. I can just quickly take you through this table, and you can go to this table and see that there are like specific calls right up over here, and you can see what you should do to make it compatible on the HPU. So it's all set out for you. You can just use this as a reference wherever you see an error, and then just take whatever the step you need to do to migrate it on HPU. So this is how you would be able to handle for HPU mismatch. The HPU match and HPU modified are already handled for you. So let's just go back to the notebook just to see our training. So yeah, I think so. It's almost halfway through, and once this gets completed, what happens is it's just going to run it for like one epoch. But the whole goal for this was to make you give you a gist about how this is handling the calls from CUDA directly to the HPU. So all you had to do was just introduce 2 steps, and this would take care of the model migration for you. Yeah, the point is like I'll move forward. There's no point waiting for the whole epoch to run. It would just take, I think, so a couple more minutes. But I think so we have seen what specifically things that we wanted to see up over here. And in the next part of our demo, I want to give it to Mohit, who would walk through the large language models and Hugging Face. Yeah, Mohit, over to you.
Thanks, Sarsh. All right, I'll share my screen. So today we're going to talk about large language models and Hugging Face, and how we use Hugging Face to train these large language models on Gaudi2. So I'll be walking through a quick notebook where we see how to run fine-tuning on these models. And then once you have a trained checkpoint, we can run inference on that. And we'll be doing a summarization task using this large language model that we just trained. And we'll see the output of that. So moving on. So this chart here, it shows about how the number of parameters have been increasing in the recently released large language models over a period of time. You can see there is exponential growth with the number of parameters. The recent models that are very popular out there, they're almost hitting 1 trillion parameters plus, and this trend is expected to continue. So current hardware solutions, they cannot hold an entire model for efficient training. So we need some clever ways or some different techniques to be able to train such large models going forward. Some of these techniques are splitting the data set, splitting the model itself across different nodes, or you could optimize the training parameters and distribute it effectively. That's where deep speed comes into the picture. So what is deep speed? So deep speed is a library from Microsoft. It's an optimization library, and it helps making distributed training really easy, efficient, and effective. So if you see this software stack on the right, you have your DL models, you have a regular training framework like PyTorch or TensorFlow, and DeepSpeed, this training optimization library, it sits right in between them. So what it does is it's just like a API wrapper. You just wrap your regular PyTorch API with the DeepSpeed API, and you're good to go. And it manages all your optimization updates and your scaling very effectively in the behind the scenes. You don't have to do anything. You don't have to take care of it. It manages it very effectively. How it does that is it partitions the various model training states across all the devices, across all the available HPUs in our case. So let's say I run a training script on multiple HPUs without DeepSpeed. This is how my memory usage would look like. All my HPU cards will be fully occupied, and their memory would be used all over. But when I use this zero optimization technology that DeepSpeed provides, these training states, they are split across all the cards, and there's a lot more memory space available. And this helps in scaling, basically, so you can train larger and larger models with large parameters, and also it helps with throughput. Also, this is a very easy technique. You don't have to do much. Like I said before, you just have to wrap the API with the DeepSpeed API, and you can configure all the settings with one single JSON file. You don't need to do any model code changes. You can take your training script as is, and just with a couple of changes, you can move with the DeepSpeed. So here I'm going to walk through a code example on the kind of changes that you need to be able to run DeepSpeed with Habana. So usually we start with here. We install this special Habana DeepSpeed fork, which you can find on the GitHub of habanaai.com. This is a special fork only meant for Habana Gaudi devices. So we start with this step. Moving on. So if you have your training script and you need to target the Habana Gaudi processors, this is how you do it with the blue, whatever the blue text says here. You import this special library and then target your device by calling this device equal to target.device HPU. Now your training script will be able to target the Gaudi processors. And the rest of the stuff is just regular stuff, like you declare your model. And how you introduce DeepSpeed here is you just start with this DeepSpeed.initialize call, and you pass in your model, which you just declared before, and all the training parameters that were used for this model. You can pass all of these into this DeepSpeed.initialize API call, and it will give you a model engine and an optimizer. Now, moving on, you don't need to do anything with anything else. You just have to use the model engine for all your calls. So for example, here is a forward pass using this model engine. You just pass in your data to the model object and you get the outputs. Similarly, a backward pass, you call the backward function on the model engine object itself. Otherwise, if you were not using DeepSpeed, you would have to call this on the optimizer object. But the model engine is going to handle all of that, so you don't have to worry. And here we have introduced the Habana's mark step function call. Same thing here with the DeepSpeed. This is how you do the optimizer step function. You just call the model.step on the model engine object. Without DeepSpeed, you would have called the optimizer.step function. And again, since we are targeting the Habana devices, you need to introduce a mark step call. What this does is it triggers an execution of all the accumulated ops on your device. And finally, if you want to do distributed training with the DeepSpeed API, you just need to call this DeepSpeed.init distributed. And again, since we are targeting Habana Gaudi processors, our distributed backend should be the HCCL Habana Communications Library. And any sort of settings that you need to change for this deep speed, that can be done through this dsconfig.json file. It's a single file. We'll go through that later in the demo. And I'm using this launcher script called run deepspeed.sh, which has the use Habana flag enabled. So this will target all the Habana cards. You can see a few working examples on the website. This one is on github.com/habana.ai in the model references. There's a special folder called deep speed examples, and that should have a good working example there for you. Same thing with this one. We've enabled inference using deep speed, and that is also found in model references. There's another example with Hugging Face, and they're using their own special library called Optimum Habana, which we'll look at next. So as many of you may know, Hugging Face is a library for open source models, and they enable the democratization of AI training through a lot of libraries that they provide, like the Transformers library. And also they have this special library for Habana Gaudi processors called the Optimum Habana library. This is how it looks like. This is how you train using that. So one quick point, I want to differentiate between Hugging Face and Deep Speed. So Hugging Face is an open source model collection, and it provides libraries for training and inference. You can use this to target single card or multi-parallel card training, and it also supports Deep Speed. And Deep Speed in itself is a library just to accelerate the training and inference of large models. And in this demo, we are going to use all three together: the Habana Gaudi card with the Optimum and the Hugging Face's Optimum Habana library and the Deep Speed library. And here are some of the steps we'll be using to do that in the demo next. Excuse me. So let me go through this demo I have ready here. So we're going to look at how to do fine-tuning and summarization task using the T5 model from Google. There's an implementation provided by Hugging Face, and we're going to use that. So a little bit about the T5 3B model that we are using. It has many variants. We are using the 3B variant, which means it's got 3 billion parameters in this example. And this has been we are going to fine tune it with the CNN Daily Mail dataset, which is a collection of news articles from the CNN and Daily Mail websites. And we're going to launch the actual task using this run summarization.py. So I've already done the initial setup. I'm running this Jupyter notebook inside a Docker, inside a Habana PyTorch Docker. And this is live. So first of all, we'll start with installing the Deep Speed fork. And this is how you do it. It's pip installing from the Habana AI website. This is a special Deep Speed fork meant only for Habana Gaudi processors. Once that is done, we need to install the Optimum Habana library. And once that is done, we need to run the summarization example, which you can find inside the Hugging Face's Optimum Habana GitHub. All right. I'm gonna run this. So it's cloning this repo from Hugging Face. It'll show up here in a moment. There it is. So it has some examples. We are going to look at the summarization example. So we'll cd into that folder, which I just showed you. So this is the path right now. You can look this path up once we are done with this webinar, you can also try this on your own. So first of all, once you have the source code ready, you start by installing the requirements from here, from this example. Every example code has its own requirements. So that's going to run in the background. And we're going to look for 3 things to set up deep speed in this. We already have deep speed set up, so I'm just going to show you what to look for if to know if deep speed is ready or not. First of all is the deep speed initialize call, which is basically doing a wraparound of the PyTorch API, and it's providing you with the model engine. And then you need to run distributed training. So for that, you need to initialize the distribution using this call, API call, and targeting the Habana communications library, using that as the backend. The third point is the dsconfig JSON file to set all the deep speed training parameters. And that we're going to do here. So this is how the code looks like in our script. If you go into this run summarization.py, you'll find this. This is how they are initializing the deep speed and then using that to train the model. This is how they are using deep speed distributed API to start distributed training inside our training script. Right? All right. So let's look at where we are currently. We are inside this examples folder, summarization example. Now we need to prepare our dsconfig, which we talked about, the deep speed configuration file. It's a single JSON file that you can use to control all the deep speed training parameters. For this, for the optimizer that we are using, it's a stage 3 level optimizer, which means it can handle the most number of parameters very efficiently. There are usually 3 stages, and we are using the top stage, the most inclusive one. Let's do that. All right, so that should have prepared a JSON file here. Here it is. So we are going to run this fine-tuning example now. Everything has been done. The groundwork is ready. We are using the T5-3B model just to review. And if you're trying this on your single first-gen Gaudi cards, we recommend you update to a T5 large model instead, because T5-3B is much bigger than a T5 large model, and T5-3B only is supported on Gaudi2 for now. But for Gaudi1 users, you can go back to using T5 large. So let's go through that. Yeah, a quick note is when you run this training, fine-tuning, it takes multiple hours. So I'm not going to go through the whole fine-tuning. I'm just going to show you the command and what is important there, and what are the things that you need to be mindful about. And then eventually, I've already prepared some checkpoints from the fine-tuning, and we'll use those checkpoints to run summarization very soon. So 3 things we need to take care when we are running distributed training with Habana on Hugging Face and using deep speed. One is, first of all, you need to target the Habana devices. You use this flag. And you can use HPU graphs, which reduces recompilation. We are not covering this topic in this webinar today. Third point is you need to use some Gaudi config name file, which is coming from Hugging Face. It's telling the Hugging Face code which model that you're running. All right. So let's take a look at where we are currently. We are inside the example summarization. We create a output directory folder, FT summarization, just like to store the output from our training. And we pass this as output directory inside this command. This is the actual command that you use to run the training. So 3 things. First of all, you created an output directory. You're telling it use that. Another thing is you're telling it to use deep speed, right? This is the actual script, run summarization.py, where the model training script, where everything is happening. You specify a model name using this flag. the dataset name here. And like I mentioned, the Gaudi config name, this is for Hugging Face's code to understand this is a T5 model. And finally, the DeepSpeed dsconfig.json that we just prepared. So you can take this code and run it in a separate terminal and let it run for a few hours. What you'll get is the output, a checkpoint in this output folder. Let's look at that. So once you open that folder, once the training is completed, this is how it's going to look like. It's going to have these few checkpoints because their whole training process was very long. So it automatically generates some checkpoints. And it's going to have some configuration files and some model weights also. So now we'll be using those model weights and checkpoints to continue with our summarization task. So here we are introducing the Hugging Faces pipeline API. That's very simple API. You just import from transformers, import pipeline, import the model, and import the tokenizer. We're telling here how to load, which model to load or which model to fine tune. And this is how you initialize the model and tokenizer. In our case, we're using a pre-prepared checkpoint from the session that I'd run before offline. And this is the path for that. So I'm just going to point to that. In your case, if you directly want to use the original T5 3B model, you can just use this model equal to model to fine tune. You can just point to the model to fine tune string here instead of a local path to a checkpoint. And that's all you need to do to pass to use in this pipeline. You just need to tell what task it is, what model you're using. It could be either a checkpoint or the original model itself, the device that you're targeting, and the data type you'll be using. All right. So that's your pipe that's prepared and ready. All you need to do is give it some input text that you need to summarize. So here is our text. It's a very big article on photosynthesis. It's a pretty large article. Feel free to go through this once we are done with this webinar. And what will happen is this pipe will ingest this input text right here, like text to summarize, put it in the pipe. And what you get out is the result. So let's quickly run this and see how that looks like. It's going to download the model because this pipe needs to be ready with the model code. And it's going to take a couple minutes. So meanwhile, I'll just recap what we just did right now. So for now, we've fine-tuned a model. I have prepared a checkpoint and kept it here in this path. In your case, that path may look like this one. If you follow this Jupyter notebook as is, it will look like this once you're done with your training. And what we did again is we prepared a pipeline. We tell it, okay, I need a summarization task to be done. And what kind of model I need, I can use either the checkpoint that I just prepared, or I could use the original model. And we're targeting the device, the HPU device with the data type. I prepared a prompt, an input prompt, a big article, which I could have borrowed from a Wikipedia page or any website. And I pasted it here. And then we are going to ingest this data into the pipe, and the pipe will give us the summarization results. So let's give it a couple more minutes.
While we're waiting, maybe it'd be a good point to open up the tab here with the Gaudi2 workshop repo, so you can show the audience here that they have access to all this content.
Sure. So here's our GitHub. Let's open this page. So we have github.com, Habana AI. Gaudi2 workshop, which we have just released. I'm running the LLM training right now. Harshvardhan showed you the model migration example, and Greg had the stable diffusion demo here. So let's quickly go through those. You can access that as of now. We have the Jupyter notebooks ready to go. Just download this, clone this on your machines, start running them. Same thing with the model migration example. And I'm here with the LLM training. This is my Jupyter notebook that I'm using. Still another minute. Once the model is ready, downloaded, then the Hugging Face code can run with our task. Meanwhile, Greg, if you'd like to take a few questions on the Q&A, please feel free.
Yeah, we've we've been answering questions as they go. I think a couple good ones here. We want to talk a little bit about the Docker. You know, it's one thing we can mention is especially for PyTorch, we have our own dedicated version of PyTorch, and that's included in our Docker image. So in most cases, we recommend that when you have your own instance on Gaudi1 or Gaudi2, that you use Habana's PyTorch Docker. And the benefit there is that you get Habana's PyTorch and you get the full Synapse AI software suite fully configured, fully installed. So it really makes it easy to go. If you have a really bespoke configuration, we do have installation instructions to be able to install some of those things individually. We have Docker files to build your own Docker image. But in most cases, we really recommend that people run Habana's Docker. And our documentation shows you those install steps and the specific Docker run commands that are required. And we also, Moet, you can also show here, back at the terminal prompt, you can show HLSMI.
Right. So here I have a command called HLSMI running in the terminal. And this is showing the status of our cards. As you can see, this is the 1.10 firmware version, and this is the driver version, 1.10. These are the 8 cards on this machine. And this is the memory usage and whatever processes are running on those. This will show up here. All right. So meanwhile, looks like our model downloading has completed. Now it's churning through the actual code. It's taking the input. And now it's here you see that the Habana PT bridge configuration flags are showing up. That means Habana has been activated. The Gaudi card is running. Let's quickly look at HLSMI again. So you see this card now is busy. It's running the actual inference task. So this, when you see these flags, that's a very good sign. Usually shows that your cards are up and running. And now we're showing, hey, this is the input that we gave you. This is the input we gave to the model. It's a big article about photosynthesis, a pretty complicated article at that. And it's going to churn out a quick summary of that very soon.
Okay,
Yes,
another question we had. Another question we had while we're waiting here is about deep speed. So there was a question about deep speed being exclusive to Habana, and no. So deep speed is actually made by Microsoft. So the AI community at large has really adopted deep speed as a really a way to efficiently drive workloads and separate workloads across multiple cards and multiple nodes. So you see this in multiple architectures. You see multiple models taking advantage of deep speed. So it's an industry-wide implementation that we take advantage of as well.
Yeah, and we do have our own fork for it, so definitely. All right. 2 more seconds, I guess. yeah, there is a small latency with the pipeline API that Hugging Face uses. There are other methods to do that, to run this kind of inference without using the pipeline API. For that, I would refer you to the Hugging Face Optimum Habana examples website, like this one, where we just git cloned it. You can find other examples there to do this inference. For now, we should be getting our answer very soon.
Okay, there was another question about Gaudi2 access. So here at the end of the presentation, we'll have a link to sign up for Gaudi2 on the Intel Developer Cloud. And yes, it is able to be rented on an hourly basis, and the current cost of that will be listed in the website. And then for people interested in engaging with Supermicro for the actual chassis, we can get you in touch with our sales team and get you the latest pricing.
All right, just in time. We got the result now. So we gave the model an input task, and we asked it to summarize this huge article. And it's given us a nice summary here in a few lines. As you can see, you find this insightful. And you're welcome to try this demo and change the input prompt. We have given you 2 prompts as part of the notebook. You are welcome to try any prompts. These are very complex articles, and the model usually gives a nice output like this, summarizes the whole text in a few lines. And yes, once you're done with using this card or this notebook, you need to run this exit code. So that will give up, as you saw, it just gave up on that card. The card stopped running. Otherwise, your card might have stayed busy with the Jupyter because it was busy with the Jupyter node. All right, so that was summarization demo using Hugging Face. And I'll hand it over to you, Greg.
Okay, just stay with this, and you actually, yeah, I'll share.
Sure.
Right. So now that you've seen all this, where can you go? We want to really, now let's drive you guys as users into where to get this information. So if you want to run pre-configured models and run these examples and tutorials, you can go to our model references page, which we've been showing you. We also have a set of solutions that are some real-time workloads, including a nice chatbot using the Gaudi 2.0 large language model, and our tutorials, which are some from very simple to very complex. As well as if you're looking to run Hugging Face models, you can go to the Optimum Habana repository and see this summarization example, as well as other examples. If you want to look more in details of how to do the model migration, how to run our Docker and install it, details on multi-card and deep speed usage and additional performance and debug, you can refer to our documentation. So we have a specific PyTorch model porting guide, which will take you directly to all the steps we reviewed today. So these are some resources for you to move forward. Now to close, the call to action is really, let's just start using this. Yeah, use the content, use the material. We'd like you to sign up for the Intel Developer Cloud. So we have a page here at our developer website that takes you directly to the Developer Cloud. And for those, everything you saw today here, you can also run on Gaudi1 or our first gen Gaudi. So you can access that today on AWS. And the notebook, as we just showed from today's session, is also here. And for practice, there's a couple things that you can do. One is we have a very simple training deep speed model called MinGPT that we have in our tutorials, which is a really nice way to get familiar with the deep speed setup and seeing the 0.1 and 0.2 configurations. And you can also practice the GP migration steps that Harshvardhan showed on some very nice PyTorch examples here. So they are available, and you can run them and see the migration at work. And then finally, for those of you outside of today, when we're done, you can engage with us at our user forum. So forum.habana.ai. So this is a place to post questions. These questions will come back to us in the application engineering team. and we'll be able to continue the conversation and continue and engage. Okay, so thank you for being part of this. When we close, there will be a small 2-question survey. I will take a few moments to look at the final list of questions that we didn't get to. How are the multiple Gaudi cards connected to the host system? So in this case, our server, the full server has 2 Intel CPUs, and those are connected over PCIe. So those are connected over PCIe bridges to the 8 cards. So each server has 2 CPUs and 8 Gaudi2s. What is typically used for running distributed systems and making them available to the libraries? Would Kubernetes be used? Yes. So in some cases, when you look at large nodes and large clusters, we would support Kubernetes, and we have instructions on how to do that. Okay. Okay, Tristan, well, we can talk with you offline. Yeah, and we'll put those links in the Q&A before we kill the meeting. All right, so I'm going to stop the share. So if there's any final questions, we'll give it about a minute to post in the Q&A window. Well, I put those final links into the chat. Okay, what's the chatbot example? You mentioned it in the slide. Let's pull that up. And I will share my screen again, just a moment. Okay, so in our GitHub page, we have our Gaudi tutorials. As I mentioned, we have Gaudi tutorials and Gaudi solutions. In our solutions, we have Gaudi chat. And so this is a chatbot using the Fast Chat API, running the DALL-E 2.0 model. So in this case, you can come in here and follow these instructions, and you will have your own built-in chatbot. The recorded lecture link will be on our developer webpage. We've had a couple questions about power comparison compared to A100 and FP32 and FP16. We typically don't publish any FP32 values because FP16 is just a superior solution and we get better performance. So there's really, everything we do, except for maybe a couple minor exceptions, we're using FP16. Or excuse me, we're using bfloat 16. bfloat 16 is what we use. And we rarely publish anything in FP32. Okay, so if the cards are connected to the host system via PCI Express, what's the purpose of the onboard Ethernet? So we remember that in this case, in the single chassis, the Gaudi cards are connected to the CPU, but then to scale out and to scale from card to card, each card is connected over gigabit Ethernet. And then outside of the chassis, for each server to connect to the next, those are also then using Ethernet. So again, instead of depending upon the latency of a third-party Ethernet card and the cost of a third-party Ethernet card, all of that is on package and on die. So that drives better performance and lower cost. Okay, so we're about 8 minutes over. So again, what I recommend everybody do is go to our forum. In this case, this is forum.habana.ai, and you can post any question you want here regarding training, inference, or system setup, or general questions. So if you have any additional questions, come in here to general questions and post these, and one of us on the team will gladly answer them. So thank you all for your time. Hope you enjoyed this. Please take the survey as we end. You'll see a survey pop up in just a few moments. So again, have a great day. And thank you all. And we'll end the content now. Thank you.